Hello everyone, I am Bireshwar Roy. I am currently pursuing my fourth year PhD in the Department of Physics, Indian Institute of Science, Bangalore. In this NPTEL GATE Physics course, I will be discussing some previous year's GATE Physics questions and try to solve them with proper explanations. This question was asked in the GATE Physics paper 2020. This is a numerical answer type question having 2 marks, and the topic of the question is quantum mechanics. The question is, a hydrogen atom is in an orbital angular momentum state Lm where m equals to L. If the angular momentum vector L lies on a cone which makes a half angle 30 degree with respect to the z-axis, then the value of L is, so you have to find the value of L here. Let us see how to solve this problem. So for an orbital angular momentum state L and M, we have mod of Lz equals to mod of L vector times cos theta. So basically our L vector is making an angle theta with the z axis, and this component along the z axis will give the Lz. Now the eigenvalue of the Lz for this Lm state is mh cut, and the eigenvalue of the orbital angular momentum vector, that is L, is root over L into L plus 1 times h cut. So we will use these eigenvalues in this equation. So we will get mh cut equals to root over L into L plus 1 times h cut times cos theta. According to the question, it is given that the state is L comma m where m equals to L. Again, the orbital angular momentum vector L lies on a cone which makes an angle 30 degree with respect to z axis. So we'll put m equals to L and theta equals to 30 degree in the previous equation. So we'll get L h cut equals to root over L into L plus 1 times h cut times cos 30 degree. So h cut and h cut will be cancelled out from both the side, and we'll get L equals to root over L into L plus 1 times cos 30 degree, that is root 3 by 2. Now we'll square both the side, so we'll get L square equals to this term root over L into L plus 1 times root 3 by 2 whole square. So L square equals to L square plus L times 3 by 4. Hence we will get 4L square equals to 3L square plus 3L, and from here we can get L equals to 3. So this is our answer. So according to our solution for this state L comma m where m equals to L, the value of the L is 3, in which the angular momentum vector L lies on a cone which makes a 30 degree angle with respect to z axis. This question was asked in the GATE Physics paper 2020. This is a numerical answer type question having 2 marks, and the topic of the question is quantum mechanics. The question is, an electron in an hydrogen atom is in the state n equals to 3, L equals to 2 and m equals to minus 2. Let Ly cap denote the y component of the orbital angular momentum operator. If del L Ly cap whole square equals to alpha h cut square, then the value of alpha is, so we have to find the value of alpha in this equation. Let us see how to solve this problem. So before going to the main solution part, we will be discussing some mathematical formulation of operators which will be useful in our solution part. So let us discuss this first. The state of the electron in the hydrogen atom is L comma ml. So basically this state is orbital angular momentum state. Now we define the raising operator as L plus cap equals to Lx cap plus IL by cap, and lowering operator is L minus cap equals to Lx cap minus IL by cap. In terms of this raising operator and lowering operator, we can represent our Lx cap and Ly cap. So Lx cap will be L plus cap plus L minus cap divided by 2. Ly cap is L plus cap minus L minus cap divided by 2y. So it will be I by 2 times L minus cap minus L plus cap. Now when this L plus cap operator acts on this state L comma ml, it will give the value root over L minus ml times L plus ml plus 1, and with this state L comma ml plus 1. So basically this operator L plus acting on this state L comma ml will raise the value ml by 1. That's why it is called raising operator. And when L minus cap operator will act on the state L comma ml, it will give root over L plus ml times L minus ml plus 1 times this state L comma ml minus 1. So basically this operator L minus acting on the state L comma ml is lowering the value of ml by 1. That is why it is known as lowering operator. Now let us see what is the value of this element, that is L plus cap operator is sandwiched between state L comma ml dash and L comma ml. So L plus cap operator will act on this state L comma ml and it will give this value h cut times root over L minus ml times L plus ml plus 1, and it will give a inner product between L comma ml dash and L comma ml. So as all the L and ml states are orthogonal, so the inner product will give delta of ml dash comma ml plus 1. So this value will be 1 when ml dash equals to ml plus 1, and it will be 0 when ml dash is not equals to ml plus 1. Similarly, this matrix element, that is L minus cap operator sandwiched between these two states L comma ml dash and L comma ml, it will give h cut times root over L plus ml times L minus ml plus 1 times this delta function ml dash comma ml minus 1. Now this matrix element value, that is L plus cap operator whole square sandwiched between these two state L comma ml dash and L comma ml, it will give h cut times root over L minus ml times L plus ml plus 1. So basically it is coming when we are acting this L plus operator on this L comma ml state. So remaining term will be L comma ml dash state, and L plus cap is sandwiched between these two state, that is L comma ml dash and L comma ml plus 1. So this state is already raised by 1 because of this operation L plus 1 by 1 time. So after this operation we will get h cut square times L minus ml times L plus ml plus 1 times L minus ml minus 1 times L plus ml plus 2 to the power half, and it is multiplied with this delta function, that is delta ml dash comma ml plus 2. So it will be non-zero when ml dash equals to ml plus 2. Similarly, we can find this matrix element, that is L comma ml dash and L comma ml, where L minus operator square is sandwiched between these two state. So it will give h cut square time L plus ml times L minus ml plus 1 times L plus ml minus 1 times L minus ml plus 2 whole to the power half times this delta function, that is delta of ml dash comma ml minus 2. So it will be non-zero when ml dash equals to ml minus 2. Now we have to find this quantity, that is del Ly cap whole square. So this means basically expectation value of Ly cap square minus expectation value of Ly cap whole square. Now we'll find this expectation value of Ly cap. So this means Ly cap is sandwiched between this same state, that is L comma ml. Now we can represent this Ly cap as I by 2 times L minus cap minus L plus cap in terms of the raising and lowering operator that we have seen in the earlier slides. So we are getting I by 2 times this element, that is L minus cap sandwiched between this LML state, and that is expectation value of L minus operator. Similarly, minus expectation of L plus cap operator. Now L minus state operating on this state LML, it is lower the state and it will give a state L comma ML minus 1 with some prefactor. But because of the orthogonality, the LML state inner product with L comma ML plus ML minus 1, it will give 0. Similarly, for this case also we will get 0. So it will be I by 2 times 0 minus 0. So essentially the expectation value of the Ly cap operator will be 0. Now Ly cap square, this operator can be written as I by 2 times L minus cap minus L plus cap times the same thing, that is I by 2 times L minus cap minus L plus cap. So after multiplication we will get minus 1 by 4 times L minus square minus L minus L plus minus L plus L minus plus L plus square. Now the L plus times L minus operator equals to Lx cap plus Ily cap minus Lx cap minus Ily cap. So basically we are writing this L plus and L minus in terms of Lx and Ly. So after multiplication we are getting Lx square plus Ly square minus iota times this commutation of Lx cap comma Ly cap. Now this commutation value is iota h cut Lz. So we can write L plus L minus operator is equals to L square minus Lz square plus h cut Lz. Similarly, we can find this thing L minus L plus equals to L square minus Lz square minus h cut Lz. So essentially after putting this thing in the main expression of Ly square, that is minus 1 by 4 times L minus square plus L plus square minus of this L minus L plus, that is L square minus Lz square minus h cut Lz minus L plus L minus, that is L square minus Lz square plus h cut Lz. So after doing all calculations we are getting Ly square equals to minus 1 by 4 times L minus square plus L plus square minus 2L square plus 2Lz square. So basically Ly square equals to half of L square minus half of Lz square minus 1 by 4 L plus square minus 1 by 4 L minus square. So we need this to find the expectation value of Ly square. So we have Ly square equals to half of L square minus half of Lz square minus 1 by 4 L plus square minus 1 by 4 L minus square. So the expectation value of Ly squared is this. So we'll use the expression for Ly square here. So we'll get 4 terms because there are 4 terms in the Ly square in this expression. So we'll get half of expectation value of L square minus half of expectation value of Lz square minus 1 by 4 of expectation value of L plus square minus 1 by 4 expectation value of L minus square. Now we have seen this expectation value will be non-zero when this ml value is basically 2 times greater than this ml. So but here it is same, so it will give 0. By the same reason this element will also be 0. So effectively these two terms will be 0, but these two terms, first two terms will survive, and expectation value of L square is L into L plus 1 times h cut square, and expectation value of Lz square is basically m h cut whole square. So we'll get half of L into L plus 1 times h cut square minus half of ml h cut whole square, and other two terms will give 0. So what we have, the expectation value of Ly square equals to h car square times L into L plus 1 minus ml square. So this quantity, that is del of Ly cap whole square, is basically expectation value of Ly square minus expectation value of Ly whole square. So this expectation value Ly is 0, so the surviving term will be expectation value of Ly square. This will give h car square by 2 times L into L plus 1 minus ml square. So our del of Ly cap whole square is basically h car square times L into L plus 1 minus ml square. So this is the expression for general state L comma ml. Now it is given in the question n equals to 3, L equals to 2 and ml equals to minus 2. So we need these values L and ml. We'll put this in this equation. So we'll get del of Ly whole square equals to h car square by 2 times 2 into 2 plus 1 minus 2 whole square. So it will give h car square by 2 times 6 minus 4, and we'll essentially get h car square. Now it is given in the question, that is del L y cap whole square is equals to alpha h car square. Here alpha equals to 1 from our result. So the final result is alpha equals to 1. So according to our solution for this electronic state in the hydrogen atom, that is n equals to 3, L equals to 2 and m equals to minus 2, the value of this del L y cap whole square equals to h car square. So the alpha value will be 1 in our case. This question is from the GATE Physics paper 2020. This is a MCQ type question having 2 marks, and the topic of the question is solid state physics. Specifically, this question was asked from the chapter lattice vibration. The question is, consider a two-dimensional crystal with 3 atoms in the basis. The number of allowed optical branches, that is n, and the acoustic branches, the number of acoustic branches is m, due to the lattice vibrations are. So there are 4 options given. The value of n equals to 2 and m equals to 4. Option B, value of n equals to 3 and value of m equals to 3. Option C, value of n equals to 4 and value of m equals to 2. And the last option, option D, the value of n equals to 1 and the value of m equals to 5. So let us see how to solve this problem. Now let us discuss the number of phonon branches in a solid. Let the number of atoms in the primitive cell of the solid is P. So basically the number of bases in the primitive cell is P. Now let us follow this chart. For one dimension, the total number of phonon branch will be P, where P is the number of bases. Now in one dimension only one acoustic branch is possible, so the remaining phonon will be in optical branch. So number of optical branch phonon will be P minus 1. Now for two dimension, total number of phonon branch will be 2 times P, where P is the number of bases. So basically we have to multiply the dimensionality of the system with the number of bases. So total branch will be 2p in 2 dimension. In 2 dimension only 2 acoustic branch is possible in either x or y direction. So the remaining phonon number of phonons in the optical branch will be 2p minus 2. In 3 dimension the total number of phonon branch will be 3 times p. So acoustic branch phonon will be 3. So basically the acoustic branch number of acoustic branch phonon is depends on the dimensionality of the system. So it will be 3 here. So number of optical branch phonon, that will be remaining phonon branch, that will be 3p minus 3. Now it is given that the given crystal is 2 dimensional with the number of bases is 3, that is p equals to 3, and the dimensionality of the system is 2. So total number of phonon branch will be 2 times 3, that will be 6. As it is 2 dimensional system, so number of acoustic branch will be m equals to 2. So remaining phonon branch will be in the optical branch, so that will be number of optical branch n equals to 6 minus 2 equals to 4. So this set n comma m is basically 4 comma 2 in our case. So option C is correct. So the number of allowed optical branches and the acoustic branches for this two-dimensional system, crystal system with 3 atoms in the basis is 4 comma 2. So option C is correct for this question.